we were plugging in positive root 3 for t to find the slope of the tangent line there. So 3 halves positive root 3 minus 3 halves, and I was going to just go ahead and write that as a fraction. This more than likely would have been a calculator active question because that, is pretty hairy. But there's one slope of the tangent line. We also have a second t value of negative root 3, and so we would just plug it in, 3 halves times negative root 3 minus 3 halves over negative 1 over root 3. So we'd have two tangent lines, y minus 0 equals, we'll call this dy dx sub 1 and this dy dx sub 2. But this is a number, whatever this number is, we wouldn't put the equation in there, we would find the number, but that would be the slope. That way I don't have to copy all that mess down. And this would be times x minus 3, there would be 1, and then y minus 0, and again this would be some real number that we would have found already that we would sub in there. I'm just trying to save time on the video. Alright, so let's look at part B. Find the point C where the tangent line is horizontal or vertical. Okay, so if we have a horizontal tangent line, remember that is where dy dx equals 0. If we have a vertical tangent line, that's going to be where dy dx is undefined or does not exist. Now dy dx for us, before we kind of cleaned it up here, was a rational expression. It was dy dt over dx dt, a rational expression. Well, any fraction is going to equal 0 when its numerator equals 0. Any fraction is going to not exist or be undefined when its denominator equals 0. So we can take a shortcut right here and simply set dy dt equal to 0 for our horizontal tangent lines. Dy dt is 3t squared minus 3. So that's going to equal 0. We'll factor really quickly 3 out, divide both sides by 3. T squared minus 1 equals 0. T squared equals 1. T equals plus or minus 1. Now, part B says find the points on C. It didn't say find the t values. It said find the points on C. So those points are going to look like x of 1, y of 1. So we're actually going to find those numbers. We'll put 1 into the x function, that's 1 squared, so that's 1. And we'll put 1 into the y function, that is 1 cubed, or 1 minus 3 times 1, so that's negative 2. All right, so there's one point, and then the other point comes from x of negative 1, y of negative 1. We'll do that quickly. Negative 1 squared is 1. Negative 1 cubed is negative 1. Negative 3 times negative 1 is a positive 3. So negative 1 plus 3 is a positive 2. So there are the 2 points. There are 2 points for where the tangent is horizontal. Now we'll come and finish part B. We're going to be undefined only when the denominator of that rational expression equals 0. So now we're going to find dx dt, which if you can come back up here is just simply 2t. We're going to set that equal to 0. That only happens when t equals 0. So we have one point. We're going to plug 0 back into both of those parametric functions. And we only have one point where the function has a vertical tangent. All right? So that pretty much should get us through parts A and part B. Let me get rid of this work and we'll work on part C. Determine whether the curve is concave upward or concave downward. Concavity is attached squarely to the second derivative. Remember, that is a 3-part process. You take the derivative with respect to t of dy dx. You just look back up to your part A, you've already found dy dx. And now divide that. The third step is to divide that by dx dt. So we want the derivative with respect to t. We said dy dx was 3 halves t minus 3 halves t to the negative 1. We're going to take the derivative of that with respect to t, and then we're going to divide that result by dx dt. So the derivative with respect to t here in the numerator is 3/2 minus, this is a power rule here, pop my negative down front, -1, and then subtract by 1. So there's my power rule, and dx dt is simply 2t. So there's a lot of cleaning up there to do, but as far as concavity is concerned, if you'll remember, the process is to set that second derivative equal to 0, find out what your critical points are. Our critical points, ladies and gentlemen, are with respect to x. Okay, so your test points are going to be x values, or even x and y values, according to what t is, and then you would test, and you would want to know where the sign changed on the second derivative. Let's see, 3/2 divided by 2t plus 3/2, so that's actually 3/2t squared divided by 2t. That's 3/4t plus 3/4t cubed. Really, really, really feel like this would be a calculator active question. But remember, if you have ratios, if your t's are in the denominators of fractions, we are going to solve that by putting one term on one side and the other term on the other. Then we're going to cross multiply kind of thing. Actually, what we're doing is multiplying by a lot of well-chosen ones is actually what we're doing. So -12t, we would have 12t cubed plus 12t equals 0. We would factor out a 12t. That would leave us a t squared plus 1 equals 0. So where 12t equals 0, or where t squared plus 1 equals 0, this is not contributing to our zeros at all, because we can't take any number, square it, and add 1 to it and get 0. So this will never equal 0. So the only t value we have to worry about here is when t equals 0. And in a prior part of the problem, we already found that that happens at the point 0, 0. So we have one potential inflection point. We could check to see what was happening on either side if we wanted to. We would see what the second derivative was doing according to those values. It might be just as easy to go back up and pick some of the other points, which I think we already did, where t was -1 and where t was 1. Find what those x values were. I think it was like 1, -2, and 1, 2. Plug those in here, plug those t values in here, and find whether we're positive or negative. I'm not going to spend any more time on this. This is calculus we already know. So I'm going to move on to the next slide. But you get the idea that that's how we would determine concavity. Okay, so let's say we have a function that is defined to be this set of parametric equations. This is the same thing as what I've been telling you. If I give you a function x equals f of t, and I give you a function y equals g of t, this is just alternate notation. Okay, it is true that I could have the x behavior here and the y behavior here. So it's just different notation. What we're getting from this is on indefinite integrals and definite integrals, it turns out that if we have a function that is defined as a set of parametric functions, we can find the antiderivative of the x function and find the antiderivative of the g function, and that's going to give us our new function h of t, or the integral of h of t. So it's basically just saying we just integrate what's happening horizontally, integrate what's happening vertically, and that's our result. This is going to give us the antiderivative, just like it always has. That's what the indefinite integral means. This is going to give us the accumulated area, and we're going to use fundamental theorem, just like we always have. All right? So let's move on here. So if h of t is defined to be x equals t squared, y equals e to the negative t, then when we integrate h of t, the integral, definite integral from 0 to 1 of h of t dt is just like we saw on the last slide. It's going to be the integral from 0 to 1 of t squared dt, comma, the definite integral from 0 to 1 of e to the negative t dt. And then we would just close those parentheses. And then we would just do the calculus that we know, the calculus that we're comfortable with, step by step by step, using that new notation. There's fundamental theorem, right? And I'm showing the AP reader that I'm fixing to do fundamental theorem part 1. So 1/3 1 cubed minus 1/3 0 cubed. There's the first one. And then negative e to the negative 1 minus negative e to the 0. There's the second one. And again, that would be in parentheses. So here we would have 1/3, that's the accumulated area horizontally. And here we would have negative 1 over e plus 1, that's the accumulated area vertically. All right, so I think on part A here, I'll call this part A and I'll call this part B. I'm not going to go, I don't think, through all the minutia of both parts of these. I'll just do the setups and you'll get the definite idea. I would like for this to be the last video in on this lesson, so I don't really want to go in minutia through this whole problem. But this says the diagram shows the curve with parametric equations x equals t squared plus 1, y equal t cubed minus 4t. So part A says find the values of t at the points A, which is 1, 0, and B, which is 5, 0. So that's fairly straightforward. What is t when x equals 1 and y equals 0? That's the first part. The second one says what is t when x equals 5 and y equals 0. So we have relationships between x and t. So let's just plug that in. When x equals 1, t squared plus 1, let's subtract 1 from both sides, t squared equals 0. So t would have to equal 0. When y equals 0, we have t cubed minus 4t. We could factor a t out of there. That's t squared minus 4. Set each of those factors equal to 0, and we get t equals 0 and plus or minus 2. So we have 3 different values here, either 0, positive 2, or negative 2. So that's for point A. On point B, we're going to do the exact same kind of thing. We're going to take our x function, we're going to set it equal to 5, and then we're going to take steps for finding those values. We've already done this. We know that when y equals 0, t equals 0 or plus or minus 2. All right? So the t values at this point are the t values that they have in common. So this is only t equals 0. Here, the t values that they have in common are only t equal plus or minus 2. So there's part A. Let's work really quickly through part B. Find the area of the region enclosed by the loop of the curve. Notice that we have an upper loop and a lower loop. So the big kicker here is that you would have to split those t values up. Here's the lower loop from negative 2 to 0. But we still have the definite integral of our x value and y value for t dt. And then we would add to that, this would be 1, and then we would add to that from 0 to 2 of x of t dt. I can write that faster, so I'm going to do it that. And then 0 to 2 of y of t dt. And then we know how to do that. We did that on the last example. So this finishes up parametric equations.